Hello everyone. In this second video of Lagrangian formulation of rigid body kinetics, we are going to look at systems with more than 1 degree of freedom like the inverted pendulum on the cart, and we are going to learn how to deal with constraints, whether the constraints are non-holonomic or they are holonomic, but you cannot easily solve for some of the variables in terms of the others and eliminate the redundant generalized coordinates. As long as you can write them as something called the Pfaffian constraint, then you can incorporate them within the Euler-Lagrange equations. So we are going to look at that, which involves the rolling without the slipping example, as well as the pendulum when we don't eliminate the between x and y, one of them from the constraint, that is the length of the pendulum is constant. So first, let's look at the inverted pendulum on the cart. This system clearly has 2 degrees of freedom. One of them is the horizontal position of the cart x, and the other one is the vertical deviation angle phi for the pendulum. Here we assume that the pendulum is just a mass at the end of the massless rod with length L. The external force applied to the whole system is only this force U, right? And here, although it's shown as mu, but it's really U. And we want to find the equation of motion for the system. So first we need to find the kinetic energy. So both of them in this case are point masses. And so the only velocities exist are the translational term. So for the bob, it's going to be 1/2 mass times velocity squared. And then I can say velocity of the whatever you want to call it, bob, and then plus 1/2 mass of the block times velocity of the block. Clearly the velocity of block is x dots squared because x is the position. So that's your kinetic energy. The only thing now you have to consider is what is velocity of this pendulum here. So in order to do that, there are several ways you can approach it. One of the simplest ones is if you consider this xy coordinate and put x here and y, so let's consider this inertial frame starting from this point. So this is going to be inertial, so when this cart and the box move, really the pendulum moves, this frame stays in place. So if I ask you what is the coordinate of this pendulum in this frame, you say that, well, the x of the pendulum is x of this point O, x of the origin, which is defined by the x of the cart, and then plus this distance here, which is clearly L times sine of phi. And then y of the point is this distance here, which is L times cosine of phi. Correct? So clearly these are x and y of this point. If you want, you can call it point P, let's say, or let's use another notation because we use P for potential energy. Let's say point N. So if that's the case, then I can call this also V of N. Now, what is V of N? V of N squared is clearly x dot of n squared plus y dot of n squared, where this one is x of n and this one is y of n. And so I need to take time derivative from those coordinates. The time derivative of the first one is going to be x dot and then minus or plus L times cosine of phi times phi dot. Here we are using the chain rule. Then plus the second one is going to be negative L sine phi times phi dot squared. And if you here square this, it's going to be x dot squared plus L squared cosine squared of phi times phi dot squared, and then plus 2x dot L cosine phi times phi dot. Then this guy is going to be L squared sine squared of phi times phi dot squared. And clearly some of these two terms together, because they have all the terms similar except for sine and cosine squared of phi, when you factor L squared phi dot squared, it's going to be sine plus cosine squared, which is 1. So the summation of these two is clearly just going to be L squared phi dot squared. So your total kinetic energy is going to be x dot squared plus L squared phi dot squared, and then plus 2x dot L cosine phi times phi dot. So this is Vn, and if I plug that up here, your total kinetic energy will be, because I have x dot in both of them, so it is going to be 1/2 times m plus m times x dot squared, and then plus 1/2 m L squared phi dot squared, and then plus, here there is a 1/2, there is a 2, they would cancel out, so you will get m L cosine of phi times x dot times phi dot. So this is your entire kinetic energy. The potential energy here clearly comes only because of pendulum, because the center of gravity for the block does not go up and down. So it is only because of change in the position of the pendulum. And if you consider your x-axis to also be the datum of your potential energy, then the potential energy is going to be L cosine phi, which is y times mg, correct? So it is going to be mg times L times cosine of phi, right? And then if you subtract them, right, that's where you get your Lagrangian. So here all I need to do is to copy those terms that I had up there, right? This is for k. Then I can copy P or simply write it because it's just a small term. So now let me calculate the partial derivatives. So here note that the generalized coordinate has two components, x and phi, right? So your q here is x and phi. So when you calculate the partial derivatives, partial of L with respect to q, you have to have two terms, right? One of them is partial of L with respect to x. The other one is partial of L with respect to phi. Clearly, you see there is no direct x term here anywhere, so this is going to be 0. The only phi term is the last term, so it is going to be mgl sine of phi. And then I also need to calculate the partial derivatives with respect to the dot terms. Again, two terms here. First one is partial with respect to x dot, and the second one is partial with respect to phi dot. So with respect to x dot, the only x dot term I have is here and also here. So that makes it to be m plus m times x dot. And then this term is going to be ml cosine phi phi dot. And with respect to phi dots, you have two terms here and here. And that's makes this guy to be ml squared phi dot. And then plus ml cosine phi times x dot. So I got my partial terms, and now it is time to go and write my Euler-Lagrange equations. There are two of them again here. The first one is d over dt of partial of L with respect to x dot minus partial of L with respect to x is q of x. The other one is d over dt of partial of L with respect to phi dot minus partial of L with respect to phi is q of phi. And if I carry out the time derivatives, so the first one is time derivative of this, which is definitely going to be m plus m times x double dot. The next term has two time variable terms, cosine phi and phi dot, so it is going to be plus ml times. Time derivative of cosine phi is going to be negative sine phi. There is a phi dot involved, plus another phi dot, you get phi dot squared. And then it's going to be plus cosine of phi times phi double dot. Okay, minus partial with respect to x, which is 0. This is equal to q of x. We have to figure that out. For the bottom one, it's the partial of the bottom one, which is ml squared phi double dot. And then again here we have two time variable terms, so it's going to be plus ml. Again, it's going to be negative sine of phi. There is a phi dot, there is x dot, so we write it down. And then plus cosine of phi times x double dot. Like this. This is equal to. So the left-hand sides are both figured out. Now we have to look at the right-hand sides, qx and q phi, and here we have to look at the work done by the external terms. So when you consider this a system, right, and you look at the free body diagram of this system as a whole, what are the forces involved? Where there is the forces involved due to gravity, which they are already taken care of. And there is the external force U, and here there is no mention of any friction, any air drag or anything, so basically that's it. And as I said, the mg's are already considered. N is not doing anything in the whole motion of the system. The only force that does work is U, and that is only acting on the block for which the motion is described by X. So if I want to find the Q terms, we keep in mind that the total work done on this system is going to be U delta X, the virtual work. And clearly, if we say this is equal to Q of X times delta X plus Q of phi times delta of phi, clearly that means you set them equal, that Q of X is equal to U and Q of phi is equal to 0. So this is 0, this is going to be U, and that gives us our equations of motion that you can see here. Now, many times you rearrange these equations and you try to find them in a better way. What do I mean by better way? Well, if you look at these equations, both of them have x double dot in them and phi double dot in them. What I personally prefer, if I want to simulate this system, is I have one equation that says x double dot is equal to some function of x and x dot, and then phi and phi dot. And then I have phi double dot to be some other function of these parameters, right? If you use OD45 or any other solver, this is the format that you need to have them. And then use two dummy variables for x and x dot, two dummy variables for phi and phi dot, and convert it into 4 first-order coupled ODEs that you have to solve all at the same time. So what you really need are two equations, right? For the forward dynamics problem, where the forces are given and you need to find the acceleration terms and double integrate them to find the position, let's say. you need equations in which only there is one x double dot and there is one phi double dot. Well, here there are both of them in both equations. So one of the things you can do is you can write this in a matrix format like this, and then try to find x double dot and phi double dot based on everything else. Or you can eliminate one term in between them, but I guess the best way to do it is using basically this way that I'm telling you. So if you look, the coefficient of x double dot in the top one is m plus m, and the coefficient of phi double dot is ml cosine of phi. The coefficient of x dot in the bottom one is again ml cosine of phi, and in the bottom one is ml squared. And any term that does not have double dots, you have to take to the right hand side. So this term here has to go to the right hand side as well as this term. So that makes this to be u plus ml sine phi dot squared, and the bottom one will be 0, and then plus ml sine phi dot x dot. And now here is like a matrix A, here is like a right hand side B, and here is like an unknown, whatever you want to call it, Z. So clearly from here, your Z is going to be A inverse times B. So if you invert that, multiply by that one, that should give you the solution. So your x double dot and phi double dot are going to be inverse of this 2 by 2. You know, the inverse of any 2 by 2 matrix is you swap the diagonals and you negate the anti-diagonals. And then you divide by the determinant, which in this case is m times m plus m L squared minus m squared L squared cosine phi squared. And then you multiply that by the right hand side. And so that's what you get. You multiply the first row by this, divide, and then you multiply the second row by this column and you divide, and that gives you only functions. If you look here on the right hand side, there is only x. There is no x really, there is only x dot. There is x dot, phi dot, and phi, right? And that gives you those two equations that I just talked about, correct? So this is those set of equations that I told you. And as I said, there is no x in any of them, so they are going to be like this, basically. And you can use them for finding x double dot and phi double dot at any moment, and then double integrate them to find x and phi in the next time point, or one time integrate them with respect to time to find x dot and phi dot in the next time point. Okay, so this is how you find the equations of motion. And one big advantage that you probably noticed is because here I'm working with those forces that do a net work, I can skip the internal forces because I consider this like a system. And if I want to focus on each individual component here, you definitely know at this pin I have x and y reaction applied from the block to the mass, and then there is reaction to those which are applied from the pendulum back to the block. But since the net work done by these forces at that point is equal to 0, they will never show themselves anywhere, and so that's the beauty of this method is you can skip what? You can always skip internal reaction forces and couples that do not do a net work. So it's very similar in that aspect to the work energy method, when you consider the whole thing as a system and not individual components, and that will eliminate a bunch of unknown reactions that you don't care about, as well as you're dealing with energies and scalars, not with vectors, right? So that's the beauty of this Lagrangian method. Now, that was a system with 2 degrees of freedom, and you can apply to more and more degrees of freedom. As I said, I will be doing that in my next video, where I find the equation of motion for an n-link robotic arm using the Lagrangian method. So here we assume the robot has n links in general. It's an open chain. And then we are going to find our equations of motion that you will see. Okay, so that's the topic of next video, to go for n arbitrary links of a robot. But there are a couple of other important topics that we need to discuss about this Lagrangian. What are they? The most important one, as I said, is constraint. So constraints are the important thing. Remember that when we looked at this case where we chose 2 Q's instead of 1, because the degree of freedom was 1, and we had a constraint, one way to get around this constraint was we found one of these redundant ones based on the other one and eliminated literally that redundant parameter. Now, not always that's a possibility. If this relation between x and y is more complicated than this, in this case it's easy, you can easily find one based on the other. But if it was something like, let's say, x squared plus exponential of negative x, I'm just making something up, not that it represents something physical here, and then plus y cubed plus sine of y, and then minus 2 equals 0. If I say now find x as a function of y, you might not be able to necessarily find it. So if the equation is something like that, still holonomic but complicated, you cannot eliminate anything based on something else. You cannot solve. So how would you handle that? That's one thing. And sometimes the constraint that you have, you cannot even write them into a holonomic form. You cannot write them only between the Q's. The equations that you have, the constraint equations, can only be written between the dot terms, between the Q dots. You can never write them into a format that is only between Q's. You can never integrate them versus time completely. We call them non-holonomic constraints, or non-integrable constraint, like when some object is slipping on a surface without, rolling on a surface without slipping, right? So how would you handle that? Well, this is what we say. If we can write our constraints, whether non-holonomic or holonomic, if we can write them into this format, that a matrix C of Q times vector Q dot equals 0. Okay, so a matrix of Q's times Q dots, if I can write it to be equal to 0, which we call a Pfaffian constraint, if I can write it that way, then all I need to do to incorporate those Q's, those redundant Q's, into and constraints into my Euler-Lagrange equation is to add one extra term here, which is negative of that same C matrix, the transpose of it, times some unknown parameters. We call them the Lagrangian multipliers. These Lagrangian multipliers, if you watch my video under playlist optimization, you can see these are used in problems where I'm trying to what? Trying to really optimize a cost function, minimize a cost function, but I also have some side constraints, right? So if you remember, the goal of these equations, these Euler-Lagrange equations, was what? The goal of them is to give me Q of t that is going to minimize for me the integral of action, correct? Which was integral from t1 to t2 of what? L, which is the Lagrangian, correct? I wanted to minimize this guy. That was the goal. What q will give me minimum of that integral of action? The q that for which this Euler-Lagrange equation works or holds. Now, what I do here, I also have a constraint, and the constraint is of this format, that C of Q times Q dot is equal to 0. I have something extra that I have to satisfy. Okay? I need to also satisfy that. And since this constraint that I have is an equality constraint, then I will use the method of Lagrangian multipliers that, if you're not familiar with, please watch the video relating to that topic on my channel. It's called Constraint Optimization with Lagrangian Multipliers, which is for equality constraints. And what you do is you modify your cost function, which in this case is the integral of action. In that integral of action, what you can do is you can modify your Lagrangian to whatever it was, right? And then plus the integral of this CQ dot. I mean, like if you integrate this guy versus time, correct? If you do that, and not the or that's okay if you integrate the whole thing, and you write it as like g of t, or g of q and q dot and t equals 0. What you really do is you add that function g here, but you also add the Lagrangian multiplier lambda for that g to kind of decide on the weight of the amount of importance of each one of these. Okay, and if you have several constraints, which basically means several g's, then you have to add what? You have to add several lambda. So let's say if you have g1, g2, and so on, then it's going to be like lambda 1 g1 plus lambda 2 g2, lambda g3, and so on and so forth for as many constraints that you have. If you do that, then when you apply the Euler-Lagrange equation and you're basically taking the derivatives of the function under the integral to be minimized, not only L would appear and it will create these terms, then basically the G terms will create for you this extra term, which is lambda times C, okay? And this lambda here is a vector of all lambdas, and C of Q is coming from all of your constraints, basically, okay? So here you can write all of your constraint as C of Q times Q dot equals 0. If you have more than one constraint, then the C is, let's say your Q is n by 1, then the C is not going to be like 1 by n. It's going to be like m by n, where m here is the number of constraints. And so this 0 is going to be m by 1. So here, as I said, m is the number of constraints, and n is the number of generalized variables, is the dimension of generalized vector Q. Okay, so the C in general is a matrix, and this relation C of Q dot involves all of your constraint in a matrix format. And this lambda here that you see as a vector, this is the vector of all of those lambda 1, 2, 3, and all of those individual lambdas that I mentioned. Okay, so you can write your overall Euler-Lagrange equation into this matrix format for all of the variables into Q. And this is, of course, not going to give you enough equations, because if you remember, as I told you, if you have n variables in Q and if you have m constraints, then these equations, you know, here, they are only valid for the Q's. So here, basically, you are going to have only n equations. Right? Because you apply this for each and every one of the Q's. But how many unknowns do you have? Well, not only you have n Q's that are unknowns, So if I say unknowns, the unknowns are going to be all of the q's and all of the lambdas. So you have m plus n unknowns, n q's and m lambdas. Well, here the Euler-Lagrange equation only gives you n equation. So where do you get the extra m equation? Those are this Pfaffian constraint. They should also apply. So this C of q, q dot is those extra m equations that you have. Okay. Now let me apply that in a real scenario in one of the examples so you can see this application of constraint Euler-Lagrange a little bit better. And I'm going to apply to two different scenarios. One, as I said, is the pendulum, where I use x and y and not eliminate x from the constraint equation, directly use the constraint relation. And the other one is when I cannot even do that because my constraint is non-holonomic, like the rolling disk. So first, let's get to the pendulum. So this is my pendulum here. Let me add that for you. And here, this is my equation, A of q, but since in here we want to write it as a Pfaffian constraint, I'll take a time derivative from this. And if I do so, you will get 2xx dot plus 2yy dot equals 0. In a matrix format, remember here, I choose both x and y to be in vector q. So q is x and y. And so your q dot vector is going to be x dot and y dot. So if I want to write my constraint equation as C of q times q dot equals 0, I have to write it as, if I get rid of these 2's, which I don't need, I can write it as x and y times x dot and y dot equals 0. Right? And this is your q dot, and this is your C of q. So clearly, you see, I could write my equation by taking a time derivative as a Pfaffian constraint. This is my C of q, and it is clearly a 1/2 matrix. And here, remember, when I now write my Euler-Lagrange equation, the first one is going to be like d over dt of partial of L with respect to x dot minus partial of L with respect to x, correct? And then you have the constraint term. This is equal to q of x. So there is some extra term here that we will add. The next one is going to be d over dt of partial of lambda with respect to y dot minus partial of L with respect to y, again, plus the constraint term equals q of y. Now I combine these two equations into a matrix format, and I write it as partial of f with respect to q dot d over dt of that, which is really for these two terms, minus partial of L with respect to q, which is for these two terms, then plus the constraint terms, which I will add later, is equal to, now I combine this qx and qy into the generalized q vector, which has qx and qy. Now, what is it that I will add here? As you just saw it, what we need to add is C transpose times lambda. Now, how many lambdas do you have here? As many as the number of constraints. You only have one constraint, so you only have one lambda. So this is just going to be C transpose times one single lambda. So it's going to be C transpose of Q times one single lambda, because you only have one constraint. And what is C transpose? C transpose is the transpose of this xy, right? So this guy here is going to be like x and y, right? 2 by 1. Multiplied by lambda is equal to Q of x. So if you look at this term, when you expand it, this is going to be like lambda x and what? Lambda y. So the term that should go into the x equation is this guy, lambda x, and the term that should go to the y equation is what? Lambda y. So this guy is lambda times x. This one is what? Lambda times y. Okay? So I'm trying to tell you how to use that Pfaffian constraint and add the terms to your Euler-Lagrange equations. Good. So I got two equations here, and I can call them equation 1 and 2, but I have three unknowns. One of them is x of t, the other one is y of t, and the other one is this lambda. So I have three unknowns. And clearly I have two equations, and clearly I cannot solve unless I have a third equation. And you might say, where is your third equation? Well, this is my third equation. But am I going to use it this way? No. Why? Because when I'm going to apply equations 1 and 2, you'll see in these time derivative terms, I will develop x double dot term and y double dot term. So if I want to use my constraint equations, my constraint does not have any double dot terms in it. I will take another time derivative from the constraint, so that can give me a relation between the double dots, which are the unknowns of the problem. Okay, if you want, instead of this x and y of t, I can call them what? X double dot and y double dot. Because once I have the double dots, I can integrate them twice to get my positions. So clearly what I need is a third equation between the double dots, and as I said, I will get that by taking another time derivative from my constraint equation, which if you do, you will get x dot squared plus x double dot, and then plus y dot squared plus y double dot is equal to 0. Now this guy I call equation number 3. So now I have three equations and I have what? Three unknowns to solve. But let's go ahead and expand terms 1 and 2, see what they give us. So equation 1, what does it give us? For that, I need to first have the Lagrangian. What is Lagrangian in this case? Well, Lagrangian is K minus P, kinetic minus potential energy. Your kinetic energy is clearly 1/2 m times velocity squared, and velocity squared here is x dot squared plus y dot squared, just like what we did in the previous video. And the potential energy, if you remember, it was negative, so potential energy was mg times y minus negative L, which was y plus L basically. So this was the same Lagrangian that we did last time, but this time I'm not going to eliminate this x dot term. I'm going to use it. So here I need those partial derivatives. One is partial of L with respect to x, which is clearly 0. I need partial of L with respect to y, which clearly, if you look at here, is going to be mg. I need the partial of L with respect to x dot, which is going to be m times x dot. And I'm also going to need partial of L with respect to y dot, which is going to be m times y dot. So I need all of these four terms, and I'm going to apply them into the equations 1 and 2. So if I do so from equation 1, I will get time derivative of this term, which is going to be mx double dot, minus partial of L with respect to x, which is 0, plus lambda x equals q of x. So we have to figure out q of x. Equation 2, you will get my double dot, and then plus m or minus mg, and then plus lambda y is equal to q of y, and then equation 3 again, remember that it was x dot squared plus y dot squared plus xx double dot plus yy double dot equals 0. Right? So the only thing I need to provide now is q of x and q of y. Once I have those, I'm good. And what are those? Well, clearly here, again, I use the variational approach. So the total work done by everything in the case of this pendulum, if you remember, the only thing I have is this external torque here, right? The mg is already considered in potential energy, so it's T times del theta. But what I want here is qx and qy, so it should be like qx del x plus qy del y. So the question is now, what is qx and what is qy in here? And what you need in this case is you find theta as a function of what? X and y. So what is theta? If you know, theta here is definitely arctangent of y over x, right? As you can see, correct? This is, or it's x over y really, because your horizontal is x, the vertical is y. So it's tangent inverse of x over y, the way it is defined. And all I need to do is to now find the variation of theta, which, if you know from your calculus, it is going to be partial of theta with respect to x times variation x plus partial of theta with respect to y variation y. Right? And if I plug this guy in to this relation, then you clearly will see that from the combination of these two that your coefficient of delta x on the left is going to be t times variation of theta with respect to x. Here is going to be qx. So qx is going to be t partial of theta with respect to x, and qy is going to be t partial of theta with respect to y. And all you need is to use this function and take partial derivatives. So partial of theta with respect to x, it is going to be 1 over y, and then the derivative of arctangent is 1 over the whatever it is, over 1 plus that argument squared. Correct? And if I do so and simplify here, I will get t times y over x squared plus y squared, which you know x squared plus y squared is really L squared. So if I want to simplify it, it is going to be like t times y over L squared. And this one is going to be t times partial with respect to y. It is going to be negative x over y squared. And then again times 1 over 1 plus x over y, the whole thing squared. And if you simplify this time this one, it is going to be negative tx over x squared plus y squared. And again, if you replace x squared plus y squared with L squared, it's going to be negative tx over L squared. So these are your qx and qy in here. Let's go ahead and replace them. So this one was 0, this one is t times y over L squared, and this is t negative times x over L squared. And now I have 3 equations and what? 3 unknowns. What you really do not care is the lambda here, because all you really need is the governing equations of motion for x and y. Lambda is a byproduct, which we'll see. That's one of the reaction forces, really. Correct? In general, this lambda is a reaction force. But let's see if we can get rid of this lambda from these equations. Or, as I said, you can write your equations into the matrix format and solve for it. Because if you want, you can write your system into the matrix format, and you can then solve for your unknowns here. So if you look, I have a 1, there is no y double dot, there is a x for lambda. For y double dot, or it's m actually, then there is a 0, there is a m, and there is a y. And for the last one, there is x, there is y, and 0. And the right-hand sides are like ty over L squared. And then I guess that's it. The second one is negative tx over L squared. And then this mg will go to the other side. And the last one, you will get negative x dot squared, negative y dot squared. So you can write it this way. And then from here, you invert this matrix A multiplied by the right-hand side B. That gives you the unknown vector Z. And then the first two components of that are definitely going to be what? Going to be your x double dot and y double dot. So here, if I do a little bit of, let me show you how to do it with MATLAB symbolic, right? So the unknowns that I need are x, y, m, l, and x dot and y dot, correct? So here I go to my MATLAB symbolic and say sims x, y, m, l, x dot, and y dot. I define my matrix A, the coefficient matrix, to be equal to, and it's m0x0my, correct? So let's write it down, m0x0my, and then I had x, y, and 0. So this is my coefficient matrix, and then the right-hand side is going to be a t times y divided by L squared, and then negative, let's make sure, negative tx over L squared, negative t times x divided by L squared, and then plus m times g. Now I have to also define g as a symbolic variable, right? Because I have not defined it yet. So I define it, and then the last component is negative x dot squared, negative y dot squared, right? So this is, you see here, it's capital T. MATLAB is case sensitive, and now it doesn't recognize T because I did not define it. So here we go, right? Now B is there, A is there, and now I say inverse of A times B. And that should give me this amazing thing. Can I simplify it? Probably. I use the command simplify in the symbolic toolbox, and I'll try to see if I can get anything much simpler. I do in most of these, you see x squared plus y squared, which is simply L squared, right? So if you just copy all of this big thing here and bring it down, that can definitely be further simplified. So here we go. Still small, maybe this, yes. So these are your answers. And as I said, anywhere you see x squared plus y squared, you can just replace it with your L squared. Right here, here, and here. Correct? And that simplifies a lot of things, because if you look, this term has L squared, this term has L squared, this one does, this one doesn't, and this one doesn't. Okay, so if I want to write the final answers, your x double dot is going to be like negative m x dot, correct, which you can see here. And then the m would also cancel, so you don't need this term. And then over L squared. The next term is going to be negative gxy over L squared. The next term is going to be negative xy dot squared over L squared. And then I have negative tx squared y over ml to the 4 and negative ty cubed over m times l to the 4. So that is your x double dot. And then you have y double dot, which again, you can get it. There are two negatives there, right? So you can get rid of the negatives because it seems like the first one, not all of them. So if you do so, these two terms would go away. You will get positive g x squared divided by l squared minus yx dot squared divided by L squared. It's the second term. The third term is negative y dot squared over L squared, negative tx cubed over ml to the 4, and negative txy squared over ml to the 4. So these are the solutions for what? X double dot and y double dot in terms of everything else, which you can definitely go ahead and double integrate versus time, given the 4 initial conditions that you have, x and y at 0, x dot and y dot at 0. Okay, so this is for this system. And this approach, as I said, can be used when the constraint equation cannot be solved to eliminate one or several of these q values, the generalized coordinate based on something else, right? So even if it was not as simple as this x squared plus y squared minus L squared equals 0, you still could use this approach by introducing this Lagrangian multipliers and basically getting more equations. That's what it is, but you can always get your equations of motion here. Now, going back to what we had, the same approach can be used for non-holonomic constraints, the constraint that you cannot integrate to write them as some function of the q values is equal to 0. So you cannot write them as a of q equals 0. You should be writing them in terms of q dots. So it is going to be a function of q dots equals 0 in general, right? So something like a of q dots equals 0, where a is a nonlinear function. But here, we assume that this function a can be written as a Pfaffian constraint, c of q times q dot. If that's the case, then I can still use this same approach that I did before, and I can use those Lagrangian multipliers to make the Euler-Lagrange equations work. And as I said, non-holonomic constraints are the ones you cannot integrate versus time to get them just to be between q's. Like, for example, when you have a disk rolling without the slipping, then this no slip condition is a non-holonomic constraint. Why? The velocity of the centroid of the disk x dot is related to the angular velocity of the disk theta dot by x dot equal r theta dot, right? That's the condition for no slipping. And you cannot integrate this and simply, in general, make it to be x equal r times theta. Okay, you can make it to be delta x equal r delta theta, in general, for this case. But not always theta of 0 is 0 and not always x of 0 is 0. So here, if you have extra assumptions, yes, then you can basically convert it into a holonomic constraint, which is x equal r theta. But that's not always the case, or you can write it in this way. Okay, and you cannot really write it in general, as I said, as a complete differential of something equal to 0. If this is something like, as I said, d of a, right, a of q equals 0, then you can integrate both sides and say, well, if I integrate both sides versus time, then it becomes what? A of q equals 0, which is a holonomic constraint. When this left-hand side is not complete differential, then you cannot integrate it versus time. And this shows itself more when it is a basically two-dimensional slipping. So your disk rolls down on a plane, let's say xz plane in this case, and then you have two of these non-slipping conditions, or you have one that you can basically write it along x and y. So your no slipping condition along the direction of motion, if you decompose it along x and y, it's going to be x dot equals r theta dot sine phi and y dot equals r theta dot times cosine phi, where theta again is the angular velocity of the spin, and phi dot is basically the other rotation of this disk about the vertical axis. It's like a yaw motion for an airplane, basically. Right? So here you have two basically q's, theta and x. Here you have four q's. It's x, z, theta, and phi. And the constraint that you have are not integrable in this case. Or if, let's say, you have a robot, right, a mobile robot that you have with one tire here and then with one tire here, and here, you know, this robot cannot move. If it's a differential drive robot, this differential drive robot cannot move laterally. It can only move along this axis, which is, you can call x of the robot, x of the b, and this is like y of the b. So you can show that it is like y dot of b equals 0, which you can also describe it in terms of the inertial frame xi and yi, correct, and the angle theta. And in that direction also, this no slipping condition, no lateral motion, will be something that you cannot easily integrate and convert it into your x and y of the inertial plus the theta, the orientation of the chassis. If you want, please refer to my video on differential drive robot kinematics, and you'll see this no lateral motion condition, the explanation that why it is non-holonomic, and so on. So here I'm going to work on this example of rolling disk in 1D motion on a surface, and here, to make this problem more interesting, I make it move on an inclined surface. So what I will have here is going to be an inclined surface like this, and then I will have the disk roll down the surface from some initial condition, and I'll find the equations of the motion that probably many of you have seen in your dynamics course or so somewhere. Correct? So here what I have is the velocity of the center. I call it x dot. Parallel to the surface, the angular velocity, I call it theta dot. and it has the radius r and the mass m. And I call the angle of this inclined surface beta. Or you can call it alpha, but I'm trying to avoid alpha to not be mistaken for angular acceleration. So what do I have here? The kinetic energy K is two terms because this has rotation and translation. So there's going to be 1/2 m x dot squared, and then plus 1/2 I about the center C times omega squared, or theta dot squared. And the other thing I have is the potential energy P. You have to basically use some reference here. And what I can do is I can consider my initial point here, the initial location. I can consider this to be the atom of potential energy. So when you go down, you're going to lose potential energy. Now, how much? If you move a distance of x parallel to the inclined surface, right? Then how much you have moved vertically down. So how much is this vertical displacement? Clearly, you know it is equal to x times sine of beta, and it is downward. So the potential energy is going to be mgy, where y is negative. So it is going to be negative mgx times sine of beta. Okay? And I about the center, if it's a disk, it is going to be 1/2 mr squared. Or you can just leave it as IC for now. Good. So definitely then your Lagrangian is going to be 1/2 m x dot squared plus 1/2 I about centroid theta dot squared, and then plus, because it's minus p, but there is a negative here, so it's going to be plus mgx sine beta. That is your Lagrangian. Now, what's the constraint that you have? The constraint is that x dot equals r times, or capital R in this case, times theta dot, right? That's no slip condition. And if I want to write it as a Pfaffian constraint, I can write it as x dot minus r times theta dot equals 0. And this can be written as 1 and negative r times x dot and theta dot to be equal to 0. Clearly, this is your vector q dot. And so this is going to be your C of q. And you only have one constraint. You definitely, you know, you have two q's in this case, correct? It is x and theta. And here I'm going to incorporate this into my equations. Let me first go ahead and calculate my partial derivatives. So what is partial of L with respect to x? Right, you clearly see this mg sine beta. What is the partial derivative of L with respect to theta? There is no term, so it is 0. What is the partial derivative with respect to x dot? Is going to be mx dot. Then what is the partial derivative with respect to theta dot? That is going to be I theta dot. Good, so I calculated all of my partial derivatives, and now I'm going to use my Euler-Lagrange equation modified for the Pfaffian constraint. That will give me d over dt of partial of L with respect to x dot, which is mx dot, minus partial of L with respect to x, which is mg sine beta, is equal to, plus the constraint term, of course, plus the constraint term is equal to q of x. And then I have d over dt of partial with respect to theta dot, which is IC. There is no theta term, so it's 0, and then plus the constraint term here, or say minus 0. It's equal to that, right? So first I have to figure what are these two terms, and then what is qx, what is q theta, and then I also need to write my constraint equation in a form that it involves x double dot and theta double dot, because this is clearly mx double dot, and this is clearly IC theta double dot. And these are my unknowns, x double dot and theta double dot, plus, of course, lambda. So the term that I had to add was C transpose times lambda, and C transpose is the transpose of this guy, right? So C transpose times lambda, remember here you have only one constraint, so there is one lambda, and C transpose means 1 and negative r times lambda. So if you write it, it's going to be just like lambda and negative r times lambda. So the lambda term is going to sit here, and the negative r lambda term is going to sit here. And what is qx, what is q theta? Again, I have to use the variational approach. So the total work done on the system, the variation of that is going to be what? Well, in this case, if you look at the free body diagram of this object, right, the only forces acting on it are N, mg, the static friction, and that's it. N doesn't do any work, static friction doesn't do any work, and mg does. Correct? So, and mg's work is already considered in potential energy. So there is not really any force other than mg that is doing work, and mg is already considered. So the total virtual work is 0 here. And if that is equal to q of x times variation x plus q of theta variation theta, then clearly both of these guys are equal to 0. So now I got my two equations, equation 1 and 2. I have two equations. My unknowns are x double dot, theta double dot, and lambda. And I have two equations unless, as I said, I go ahead and take a time derivative from my constraint equation, which is this guy here. If I take a time derivative out of that, that can give me my third equation. So I'm going to do that. And what will you get? Well, it's x dot equal r theta dot, so you can also say it's like x double dot equals r theta double dot, assuming that r is constant, which it is. In this case, it's a rigid disk. So this is your third equation now. And you can write it down here. Good. So there we go. You got your three equations and your three unknowns. And if all you care about is the x motion, then you can find it. If all you care about is theta motion, you can find it. If you want lambda, you can find it, because this is three equations and three unknowns. You know your system has only 1 degree of freedom, so you could have started with x and eliminated everything else. But if not, what I can do is, as I said, rewrite these three equations into matrix format, or I can try to eliminate lambda between equations 1 and 2 and then combine the result of that with 3. So if I eliminate lambda between 1 and 2, what will you get? It's a little simpler in this case, right? Because lambda, you can find it from 1 and then multiply it by negative r and get it to 2. Or another thing you can do is multiply both sides of the equation 1 by r. That makes this lambda r, makes it negative lambda r. When you add them together, then the result is going to be lambda eliminated. So you can do it like this way as well. If you do so, then what you will get is Rmx double dot minus mgr sine beta, and then plus I about c theta double dot is equal to 0. Can call this equation 4, and now all I need is to combine 3 and 4, and that can give me the equation governing either x or theta, one of them. So for example, if I am concerned about x, right, then I can go ahead and say theta double dot is equal to x double dot over r, and then plug this guy right into my governing equation. Then that will give me what? That will give me x double dot times, here I have m times r, here I have IC over r, and this is equal to mg sine beta. Now, if I use the fact that IC is 1/2 mr squared and get rid of these m's, then you will get your, and simplify 1r here, then you will get your x double dot to be equal to g sine beta divided by 3 over 2r, or you can say 2g sine beta over 3r, which is one of the examples, if you look at my dynamics lectures, that I solved for 2D rigid body kinetics, and I got to this answer exactly. So you see, that gives you the exact same thing as your Newton equations did give you. No difference. And I could easily implement it using Lagrange, Euler-Lagrange equation with constraints. The only thing that I want to emphasize here is this lambda. What is this lambda? If I solve for lambda here, I can get a relation for lambda. But what is this lambda? Well, if you look here, if you look at your x equation, or if you look at your theta equation, either one, you clearly see your lambda here is that static friction, is this guy, with one change. What is the change here? If you take lambda to this side, it becomes mx double dot equals mg sine beta, which is the component of mg aligned x direction. And then f is in the opposite direction, but you take it to that other side, you clearly see that's also negative lambda. So if you look at this top equation, you'll see that it says mx double dot is equal to mg sine beta minus lambda, right? And this is exactly as I said, if you write the equation of summation of the forces equals mass times acceleration x. And summation of the forces in the x direction, with x being this direction here, parallel to the surface, it is going to be mg sine beta, as I said, and then minus fs. If you compare it, you clearly see this minus fs is minus lambda. So your lambda is what? Your static friction. So as the last example, we want to focus on the disk rolling on a path on xy plane and without slipping. So the velocity of the centroid is going to be v equals r times theta dot, correct? And here we assume that the disk is subjected to some external force F, which has X component and Y component, still does rolling without slipping. This velocity V equal R theta dot, you can decompose it along X and Y using cosine and sine of this angle phi. So X dot is V sine phi, Y dot is V cosine phi. If you write for x dot and y dot as dx over dt and dy over dt, right? You can write them into differential format, or you can keep them in the original velocity equations or velocity constraints. So these two constraints that you see, x dot equal r theta dot sine phi and y dot equal r theta dot cosine phi, these are the constraints of no slipping conditions. Here, my q vector includes 4 variables, and they are x and y for the position of the centroid of the disk, as well as the spin angle theta and the tilt angle phi, which shows the direction of the motion on the xy plane. So clearly I have 2 constraints here, and I can write these constraints into a Pfaffian format. So definitely I can write it as a matrix times the vector q dot to be equal to 0. As I said, this is your vector q dot, so it is going to be x dot, y dot, theta dot, and phi dot. And if you write these equations by bringing these 2 terms to the left hand side and set them equal to 0, then it's going to be 1x dot, no y dot, minus r sine phi times theta dot, and no phi dot times that q dot vector equals 0. The other one is 0x dot, 1y dot, minus r times cosine of phi times theta dot, and no phi dot equal to 0. So this is your q dot vector, and this is your c of q. Okay, so this is writing your equations, constraint equations, into the Pfaffian form. Now we go and calculate the kinetic energy, the potential energy, and the Lagrangian kinetic energy K. This guy does move in the x and y direction, or it has this velocity v, right? But if you want to use the x and y, since the centroid has x dot and y dot components, so it is going to be 1/2 times mass times x dot squared plus y dot squared. This is 1/2 mv squared. And then it has 2 rotations, theta and phi, so each one has its own rotational term. So it's going to be 1/2 I and times theta dot squared, and then plus 1/2 j times phi dot, or you can say j times theta dot plus I times phi dot. We have to define what these guys are. Or we can use I for both of them. It doesn't matter really. Right? Because we can attach a frame to the rigid body, and that's what we should be doing. Right? And then on this frame, we can have, let's say, our let's say something like this, and we can call it z of the body. And then we can have what? X of the body and y of the body, something like this, for example. This is like x of the body, and this guy here in plane is going to be y of the body. If I write it this way, then I can definitely use some subscripts instead of I and j. So I can say that for theta dot, it is about the ZB axis. So I call it I of ZB. And this one is going to be about XB. Okay, so this is your kinetic energy. 2 rotational term, 1 translation. Then potential energy here, we can consider it to be 0 as long as this guy does not tilt on the side. So as long as it keeps going vertically. So if you look from this direction of V or this YB, the coin always stays straight like this. If the coin does tilt to the side like this, and it wants to follow a circular path in general, right? That's what we call the nutation angle. If it does that, then the centroid does change height, and then you have to consider the change in gravity potential. So here we assume that it stays vertical and just follows the path, and this scenario does not happen. So we can assume the potential energy to be 0. And so Lagrangian will be the same as kinetic energy in this case. And so we need to find a bunch of partial derivatives, like partial of L with respect to x. There is nothing. It's the same as partial of L with respect to y. And that's the same as partial of L with respect to theta and phi. There is no position term in your Lagrangian, so it makes 4 of them 0, makes life a lot easier. Then partial of L with respect to x dot is equal to mx dot. Partial of L with respect to y dot is my dot. Partial of L with respect to theta dot is I zb times theta dot, and partial with respect to phi dot is I xb times phi dot. So here we go. I found all of my partial derivatives now with the constraint, and now I can use the relations that I had, this guy, and derive my equations. So if I do that, then it's going to be d over dt of mx dot, which is going to be mx double dot, minus partial with respect to x, which is 0, and then plus the lambda terms is equal to q of x. We have my double dot plus the terms due to constraint equals qy. We have partial derivative of theta dot, which is going to be I zb theta double dot, plus again the constraint terms is going to be q of theta. Let me clean that up. And I xb phi double dot again plus the term due to constraint is q of phi. So these are the Lagrange Euler equations. Now, what are the terms due to constraints? Well, it is c times lambda. Now here you have two constraints, so your lambda means lambda 1 and lambda 2, and your c has to be transposed. Your c, if you look at the dimension of it, it is 2 by 4. When we transpose it, it's going to be 4 by 2, and then we multiply it by a lambda, which is 2 by 1, so you get a 4 by 1. So the term c transpose lambda vector is going to be like this, right? And you will have 1, 0, negative r sine phi, clean that up, and 0, 1, negative r times cosine of phi, and then 0 again. Right, so when you multiply that, the result is going to be lambda 1, lambda 2, negative r times lambda 1 sine phi plus lambda 2 cosine phi,
and then 0. And each one of these terms is one of the ones that is sitting in one of those equations. So it's going to be lambda 1, lambda 2, negative r times lambda 1 sine phi plus lambda 2 cosine phi and finally 0. Right? So each and every one of those terms is sitting in one of these places. And now the question is, what are the q's? Well, here the problem is not so hard regarding that, because the total variation of the work, in this case, the only force really on the rigid body of this object that does work is the external force. The static friction doesn't do anything. Mg and n are perpendicular to the direction of motion. So you only have the F, and this F, as I said, can have X component and Y component, right? So it is going to be like F delta X plus, or Fx delta X plus Fy delta Y. And clearly you see it's like plus 0 times delta theta and then plus 0 times delta phi. So clearly this is going to be your Qx, right? This is going to be your Qy, this is going to be your Q of theta, and this is going to be your Q of phi. So here, and there we go. We got our equations. Now, do we have enough equations for all of the unknowns? So if I ask you what are the unknowns, in this case, your unknowns, there are 6 of them. There is x double dot, y double dot, theta double dot, phi double dot, as well as lambda 1 and lambda 2. So you need 6 equations, but guess what? We only have 4 equations so far from Euler-Lagrange. But don't forget that we have our constraint equations, these guys, that I can take a time derivative from them, and they will give me 2 extra equations. So what are they? One of them is this. Your x dot is equal to r times sine of phi times theta dot. And all I need is to take a time derivative from this. Makes it x double dot to be equal to, r can come out. Here we use a chain rule, so it is going to be cosine of phi times phi dot theta dot, and then plus sine of phi times theta double dot. And then similarly for the y dot term, take another time derivative, and that makes it y double dot to be r times negative sine of phi dot theta dot, and then plus cosine of phi times theta double dot. And these are my equations 5 and 6. So now I have enough equations for all of my unknowns. And now, depending on what is it that the problem is asking you to do, is the problem asking to find the double dots, then you can again arrange these equations 1 to 6 into your matrix format if you want, and then find the double dot terms and get rid of lambda 1 or 2, or maybe you can just eliminate lambda 1 and lambda 2. So it all depends on what you want to do. If you don't care, let's say, about theta, you can also eliminate theta, right? And if you just care about x and y, then you only find x and y. So clearly these equations are linear in terms of the double dot. So if you call this vector z, whatever you want to call it, vector w, then you can write equations 1 to 6 into a matrix format where the 6 by 6 matrix is multiplied by w, and that gives you a right-hand side. And all you need is to write equations 1 to 6 into matrix format. So like the first one is going to be like all you see is m x1, and then no y, no theta, no phi. There is only one lambda, no lambda 2. The right hand side is f of x. The next one again is 0 m 0 0 0 1, and then this is f of y. Then you have 0 0 I zb zb. There is a 0 here because in that equation there is no phi double dots, but now you have coefficients for lambda 1 and 2, and those are negative r sine phi and negative r cosine phi. So we have to add them here, negative r sine of phi, and then we also have negative r cosine of phi. Right? And the next one is going to be, all of these guys are going to be 0 0 0. This is going to be I x b x b. No lambdas in it, and nothing on the right hand side. The previous one was also 0 on the right hand side. And then equations 5 and 6, if you look, you have 1 x double dot, no y double dot. There is a theta double dot term which you have to bring to the left hand side, and that becomes negative r sine phi. No phi double dot, no lambda 1, no lambda 2. The right hand side is going to be r cosine phi, phi dot theta dot, and finally we have 0 1 negative r times cosine of phi, no phi double dot, no lambdas, and that other side is negative r sine phi, phi dot theta dot. Okay, and so you can call this matrix A, you can call that right hand side B. So W is going to be A inverse times B, and the first two components in W are going to be your x double dot and y double dot that you might care about. Or if you care about the lambdas, you can find lambdas too. Which, by the way, the lambdas, if you do, you'll find out they are going to be the component of the static friction under the disk. So if there is a static friction here under the disk, like this Fs, it has an x component and the y component, and you'll find them to be lambda 1 and lambda 2. So there are constraint forces like previous case. So hopefully this video was useful to you, and you learned how to apply Lagrangian to cases where the constraints are non-holonomic, or if holonomic, you cannot just eliminate redundant q parameters, right? How to incorporate those Pfaffian constraints into your Euler Lagrange, and how to handle systems with more degrees of freedom, how to find the generalized forces for them, and so on. So thank you so much for your attention. I will see you in my next video.